Welcome back to the Unit 3 of Physics class 12th, and we are dealing with the fourth chapter, Moving Charges and Magnetism. So till last time we saw how a moving charge is affected by a uniform magnetic field, as well as we also saw how electric field and magnetic field together acts on on a particle, charged particle. We saw the example of cyclotron. Okay, so in a cyclotron, we saw that the moving charge first gets affected by the magnetic field, and it starts taking up a circular path, and as and when it interacts with the electric field too, it gets accelerated, and that increases the energy that the charge has, the kinetic energy, and that was that is the principle on which the cyclotron works. Okay, where uniform magnetic field as well as an electric field has an effect on the on a moving charge. So that it's an important thing to remember that it's a moving charge only, okay, or a current passing or a current carrying material that gets affected by the magnetic field. Okay, so we stopped at Biot-Savart law. Okay, so this is where we will see, okay, how the magnetic field is, kind of what is the relation between the magnetic field and the current that is passing through a material. Suppose we are considering this, wire. Okay, and in that we are considering a line element. Okay, so this is the line element dl. Okay, so this is the line element that we are considering. This is the direction of the line element. Okay, and this point here, this is the point where we want to determine the magnetic field. Okay, and over what is the magnetic field? The direction of the magnetic field is through this plane. Okay, and its direction is going away from us inside the plane. Okay, so because this is denoted as a cross. So when we are considering just the a line element, so the magnetic field, okay, the magnitude of the magnetic field is going to be proportional to the current that the the line element is carrying, or the current or the wire is carrying, multiplied by the cross product of the line element and the distance between the line element and the point where we want to find the magnetic field. Okay, as a constant of proportionality, we include the mu 0 by 4 pi. Mu 0 is the permeability of free space. Okay, we will see what would be the value of it. So this is the expression that we get. Okay, so this then this is in the vector form. Okay, since we have a cross product over here, so in the magnitude form we can express it as the dB in mod is equals to mu 0 by 4 pi I dl sin theta by r square. Okay, this dl cross r actually becomes dl r sin theta, so r gets cancelled, and what you're left with is r square in the denominator. Okay, and over here you can see that the mu 0 4 pi, the constant that we're considering here, that the value of it is 10 raised to minus 7. Okay, so this is the permeability of free space or vacuum. So this essentially, okay, so this expression is actually the Biot-Savart's law. Okay, so this shows you the relation between the magnetic field and the current that is passing through a particular material. Over here we are considering a line element, a current carrying wire. Now we had we had already studied Coulomb's law in electrostatics, so there are some similarities and there are some differences. So the similarities are, both are long range, and they both depend inversely on the square of the distance from the source to the point of interest that we saw Okay, in the expression you can see that dB is actually proportional, inversely proportional to square of the distance. Okay, and similarly the principle of superposition will apply to both fields. Okay, the principle of superposition applies to both the fields. And then the electrostatic field is produced by a scalar source. Okay, that is the electric charge. Electric charge does not have any direction, it only has magnitude, whereas the magnetic field is produced by a vector source I into dl. Okay, so there is a direction associated with both I and the line element. Okay, then the electrostatic field is along the displacement vector joining the source and the field point. Okay, this we had seen that the direction of the electric field is always like it is along the r vector, okay, or the distance that we see, okay, between the source and the point where we want to find it. The magnetic field on the other hand is perpendicular to the plane containing the displacement vector. Okay, so you can see over here that the field, magnetic field over here is actually going through the plane. Okay, it is going through the plane, so that is perpendicular to the plane that is containing the displacement vector and the line element. And we can also see that in Biot-Savart law there is an angle dependence. Okay, since we saw it was mu 0 by 4 pi into I dl sine theta. Okay, so there is an angle dependence in the Biot-Savart law, which is not there for electrostatic case. So if a magnetic field is at any point of time, if it is parallel to the direction of the line element, okay, then your theta becomes 0. Okay, so theta is the angle between the magnetic field. Okay, it is the angle between magnetic field and the dl, the line element that we are considering. This is your theta. Okay, so if your theta at any time becomes 0, then you will not have any magnetic field at that point. Okay, so the relation between permittivity, which we use in the case of electrostatics, okay, we have used E0 in the electrostatic part. Okay, so there can be a relation built between epsilon 0 and mu 0. Okay, the permittivity and permeability of free spaces, and you can see it in this. Okay, so they are related with the speed of the light. So if you fix your epsilon 0, okay, you can find your mu 0 using this relation, and if you fix your mu 0, you can find the epsilon 0 for using this expression. Okay, so over here we consider mu 0 to be equal to 4 pi into 10 raised to minus 7. So this is what we learn about the Biot-Savart law. Okay, now using the Biot-Savart law, we can find out the magnetic field of different kinds of in different kinds of situations. So over here we are going to consider magnetic field on the axis of a circular current loop. Okay, so this is your circular, this is actually a current carrying circular loop. Okay, and its radius is r, and the magnetic field over here you can see is dB. Okay, and this is due to a line element dl. We are considering this as the dl over here. Okay, so dl is one of the line element in the current carrying loop itself. Okay, and dB has two different components. One is dBx, okay, that is parallel to the x direction, and you have dB perpendicular. Okay, so this is perpendicular to the x direction. Okay, and this axis is actually the center of this current carrying loop. Okay, so what we do in this case is that the the evaluation of the magnetic field will be actually summing up the effect of the infinitesimal current elements IDL that we had used in the previous case also. Okay, so suppose we have infinitesimal line elements associated associated to this current carrying loop. Okay, and it would be a summation of all these of all these current elements. So we are assuming over here that your I is steady, the current I is steady, okay, and this is being done in free space. Okay, so whatever constant of proportionality we use, it will be with respect to the free space. Okay, so the x-axis, as I said, would be the axis of the loop, and we want to calculate the magnetic field at point P. Okay, so x is the distance between the center of the loop to the point P. Okay, and we are considering the conducting element dl of the loop, the magnitude of dB. Okay, dB, that is a magnetic field at point P. We can give it by the Biot-Savart law. Okay, I dl cross r upon r cube, so that would be equal to mu 0 by 4 pi I dl cross r cube. Okay, so if you want to get only the magnitude of it, so we will just put a mod over here. Okay, now we can see that this is the radius of the loop, this is the distance between the center, this is the distance between the center of the loop to the point P. Okay, and so we want to know the distance between the dl and the point P, so that can be given as a small r. Okay, so that we can say r square is equals to x square plus r square. Okay, so these two are known. Okay, these two are known, this is not known, so we substitute with these for small r square. Okay, and we can also say that any element of the loop will be perpendicular to the displacement vector from the element to the actual point. Okay, so for to understand this, we can say that the element dl in the figure, okay, is in the yz plane. Okay, so if we are considering this as the x-axis, this y and this z. Okay, so any of the element that we take, line element we take, will be in the z axis, sorry, yz axis. Okay, whereas your displacement vector is going to be in the axial plane, along the axis of the loop, and it will be in the xy plane. Okay, so dl cross r will become r dl. Okay, since your dl over here, okay, dl is in the yz plane and r is in your xy plane. Okay, so that we can, the cross vector, if we write in the scalar form, we can get it as rdl. Okay, so then we can substitute that, and over there what we are left with is dB is equals to mu 0 by 4 pi I dl by substituting this for the small r square. Okay, over here you can see that dB, the direction of dB is shown over here. Okay, and we see that it is perpendicular to the plane that is formed by dl and r. Okay, it has an x component dbx and a component perpendicular to x-axis, that is db perpendicular. So when the components are perpendicular to the x-axis are summed over, they will cancel each other out and we obtain a null result. Okay, so if your components are perpendicular to x-axis, so if you get like the cross product of them, so they will cancel each other out. So from this we can see that dbx is dbx is not going to be considered for now. We are considering the db perpendicular. Okay, so the db perpendicular component is due to dl and it is cancelled by the contribution due to the diametrically opposite dl element. Okay, over here we are sorry, dbx is not cancelling out, the db perpendicular is cancelling out over here. Okay, so only the x component will okay, so only the x component remains. Any component which is perpendicular to the x-axis will be cancelling out. Okay, so the net contribution along the x-axis can be got by integrating d dx, okay, as dv cos theta. Okay, so cos theta we can give it as using the trigonometric relations, we can find it out as r upon x square plus r square square root of that. So your dBx then becomes mu 0 IDL by 4 pi multiplied by cos theta. Okay, so cos theta, and also you also had the x square plus r square beforehand. Okay, using this we are putting cos theta value over here for dBx. Okay, so over here you can see, so dBx is also dB cos theta. We first input the values of dB and then multiply the relation of the cos theta. So what we are left with is this expression. Okay, now if we do summation of the elements dl over the loop. Okay, so the loop the area that we get is 2 pi r. Sorry, the circumference of the loop we will get is get as 2 pi r. Okay, so the magnetic field at P due to the entire circular loop will be a summation of this, okay, over the entire circumference. So what we are left with is mu 0 I r square, the unit vector I, upon 2 x square plus r square, and the cube root of x square plus r square. Okay, so the above result, okay, so this result we will obtain the field at the center of the loop. Okay, if if we are trying to find the field at the center of the loop, we have to consider x is equals to 0. Okay, so over here we are find this is the dBx, okay, that we have found, and we also found b by some doing the summation over the entire current carrying loop, okay, at the distance x. Now if we are considering at the center of the loop, we consider x is equals to 0. Okay, and then b0 will be equal to, you can put your x is equals to 0 in this and then you can find it out. So what you are left with is mu 0 I, the unit vector I, upon 2r. Okay, so using this we can understand that the magnetic field lines due to a circular wire form closed loops, and this can be seen in this figure. Okay, so this is your loop, and you can see that there are loops forming over here. Okay, so these all are kind of closed loops. Okay, and they are moving away from the center of the loop. So then we can say the right hand thumb rule. Okay, we can use it over here, and you can see that the curl of the palm of your right hand around the circular wire with the fields point in the direction of the current. Okay, so this for a circular current loop, the if you curl your fingers, the right hand side, the right hand fingers, okay, around the in the direction of the current, the thumb is going to give you the direction of the magnetic field. Okay, so if you know your direction of the current, then you can find the direction of your magnetic field, and if you know your direction of the magnetic field, using the right hand rule, you can find the direction of your current in the current carrying loop. Okay, so this is the kind of the physical significance of the relation between the current and your magnetic field on the axis of a circular current loop. Okay, now we come to another another part of the effects of your current as well as magnetic field, that is your Ampere circuital law. Okay, so if you remember in electrostatics, we had learned Coulomb's law first, okay, and then we also learned Gauss's law. So which was another way of representing your Coulomb's law. So similarly, Ampere's law is another way in which Biot-Savart law can be expressed. While in Biot-Savart law, we were considering either a infinitely long, current carrying wire, or we were considering a current carrying loop. Okay. In Ampere's circuital law, we are going to consider an open space with a boundary. Okay, so over here you can see that this is a surface and this is a boundary. Okay, this is an open surface. The current, the surface, the current is passing through the surface. Okay, so it is passing through this surface that we are seeing over here. So we are considering the boundary to be made up of a number of small line elements, similarly to how we were considering for Biot-Savart's law. Okay. So now we again, if we consider a small, line element, okay, of dl, okay, and we take the value of the tangential component of the magnetic field bt at this element. Okay. So similarly, how we had also seen that there is a tangential component. Okay, when we were doing when we were learning about the magnetic force. Okay, so we take the value of the tangential component bt. Okay, and multiply it by the length of the element dl. Okay, so right now we were first talking about the tangential component. Okay, so we are going to call it magnetic field B itself. Okay, we are not going to use BT separately. And once we find for this one line element, we can find for all the different line elements, and we can add these products together. Okay, so we consider the limit as the lengths of elements get smaller and the number gets larger. Okay, so the length will become smaller and the number of the line elements become larger. So then we can say that it actually forms an integral. So Ampere's law states that this integral is equal to mu 0 times the total current passing through the surface. So this is how we express the Ampere's law. Okay, that the integral of magnetic field B and and the product of it with the length line element dl is going to be the product of the permeability of the free space and the current that is passing through the surface. Okay, so as we said, I is the total current passing through the surface. Over here, this circle over the integral actually denotes that this integral is being done over a closed loop. Okay, so but this surface is an open surface, but the boundary in itself, it makes it into a closed loop, and this loop, okay, coincides with the boundary C of the surface. Okay, this is what we are assuming. So the relation above involves a sign convention given by the right hand rule. Okay, so you can see your current is flowing in this direction. If you curl your fingers in a way that the curling actually takes place along the direction of the current that is flowing, you can find the magnetic field. Okay, the direction of the magnetic field. So over here, suppose we are saying let the fingers of the right hand be curled in the sense the boundary is traversed in the loop integral. Okay, then the direction of the thumb gives the sense in which the current I is regarded as positive. Okay, so over here, if we are considering this as a closed loop, and this is kind of the direction of the right hand that is being curled is this boundary. Okay, then the direction of the gives the direction of the positive direction of the current. Okay, so the thumb, if you curl your fingers, the thumb is going to point in the inside the plane over here. Okay, so that would be understood as the positive direction of the current. Sometimes that is why. Okay, so now since we are considering this as the loop, if you remember in the electrostatics part, okay, we used to consider Gaussian surface. Okay, so in similar manner, okay, in similar manner we can actually consider Amperian loops. Okay, and while choosing this, we can have three conditions. Okay, that each point of the loop is either where the magnetic field B, okay, we can consider three scenarios where the magnetic field B is tangential to the loop and is a non-zero constant B. Okay, so there is a constant value of B and the B is tangential to the loop, or you can have the magnetic field normal to the loop, okay, or it gets nullified and the magnetic field vanishes. Okay, so these are some of the ways where we can, these are the kind of cases where we can consider an Amperian loop. Now if we let L be the length of the loop for which B is tangential. Okay, so now we are considering the scenario where B is tangential to the loop. Okay, and IE is the current that is enclosed by the loop. Okay, then your BL, okay, because we had already explained that it's actually a closed interval or integral, okay, or integral over a closed loop, the product of the magnetic field and the line elements. Okay, so if we get the entire length of the loop as L, okay, so the product between the magnetic field and the total length of the loop, or over here part length of the loop, whichever loop that we are the part of the loop where the magnetic field is tangential, we can give it as the mu 0 into IE. Okay, so this is the current that is enclosed by the loop at that time. Then we can see that the Ampere's law enables an easy evaluation of the magnetic field. Okay, so you can see that Ampere's law, in Biot-Savart's law you needed a lot of other values also. You needed the radius of the loop. Okay, you also you need the current separately. Okay, or you also needed the distance between the center of the loop and the point where you are calculating the magnetic field. Okay, in the Ampere's law it's just a simple relation of the the length of the loop, okay, and the permeability of the free space as well as the current enclosed by the loop. Okay, so then Gauss's, as we in the similar way how we had seen in using Gauss's law, we could find the electric field for any kind of arbitrary surface. Okay, so Ampere's law we can find it for any kind of a circuital loop. Okay, so the boundary of the loop that is chosen is a circle, okay, and the magnetic field is thus tangential to the circumference of the circle. So using this law, we can, in the left hand side of the equation, since we are considering a loop, if we were considering just kind of a straight or a curved kind of just a conductor, then we can only use the length, but right now we are using a loop, so we have to use a circumference of the circle. Okay, so in the left hand side of the equation, in place of L, okay, we are going to substitute with the circumference 2 pi r. Okay, then when we do that, you get this B multiplied by 2 pi r is equals to mu 0 by I. Okay, so when you in a simpler form, you can find the magnetic field of a closed loop, okay, which is going to be equal to the permeability of the free space. In all this is being done in free space. Okay, we will see if there is another medium, what happens when there is another medium associated, later on, and this will be 2 pi r. Okay, so this is your Ampere's law. Okay, and as for Biot-Savart's law, what we had seen, okay, E is equals to mu 0 by 4 pi. Okay. Or if we are considering at a distance away from the center of the loop, okay, so when we are considering that, we get I r square upon 2x square plus r square 3 pi Oh, okay. So this is when we are considering current carrying loop. Okay, that is the Biot-Savart's law. Okay, and this is your Ampere's law where we are considering a closed loop. Okay, a closed circular loop over here. So why is it important for us to understand this Ampere's law? Okay, because the implications that we get from them are important for us when we go into the later on sections. Okay, so how are they different and how are they kind of affecting us? So Ampere's law, or the result that we found previously, okay, that this result, we are talking about this result over here. So the result implies that the field at every point on a circle of radius r, okay, with the wire along the axis is same in magnitude. Okay, so if we are considering, a circle over here, okay, if we are considering a circle, okay, and its radius is r, okay, so at every point on the circle, okay, so at every point on the circle, okay, the field of the magnetic field, okay, at every point on the circle is going to be same in magnitude. Okay, magnitude. Why? Because suppose we are considering the tangential component of all these magnetic fields, you can see that the direction is constantly going to change, okay, but the magnitude remains the same. Okay, so what we can say from this is that the magnetic field has a cylindrical symmetry. Okay, and we can say that the field that normally can depend on three coordinates depends only on one, that is the r. Okay, if there is symmetry, then your solutions will be simple to be deduced or expressed. So the direction of these fields, okay, how you represent the field over here, it only depends on the r. Okay, this is the only coordinate, that is why this has a cylindrical symmetry. Okay, it like you don't need XYZ component for this, you only need the r. Okay, so this is a cylindrical symmetry. The field direction at any point on this circle is tangential to it, as I explained before. Okay, if you consider the field at this point, okay, so the direction would be tangential. So this is the direction of the B over here. But if you are considering it over here, okay, so this is going to be tangential over here. You see that the direction has changed. So the field direction at any point on this circle is going to be tangential to it, tangential to the circle. So the lines of constant magnitude of magnetic field form concentric circles. Okay, so suppose you find there are few points that are over here. Okay, and if their magnitude is same, okay, they can form another constant a circle, okay, a loop. And similarly, if as you go away from the center, okay, you can get these concentric circles or concentric lines, where, and these are called the closed loops, okay, where your magnitude would be the same. Okay, so that is how, remember we had seen the example where if you keep iron filings on a piece of paper and you bring a magnitude close towards it from the opposite side of the paper, okay, so the iron filings will start making concentric circles. Okay, so this is the reason. Okay, this is the explanation of how we get the concentric circles, which is not like the electrostatic field lines, okay, which originate from positive charges and end at negative charges. Okay, so the magnetic field, the direction of magnetic field, the relation of it to the the kind of the positions is different from how it is seen in the electrostatic field. So the expression for magnetic field of a straight wire provides a theoretical justification of the Oersted's experiments. Okay, we had also talked about the Oersted experiments in the, I think, previous class, so you can, revisit that. So the another interesting point that we can see is that even though the wire is infinite, okay, the field due to it at a non-zero distance is not infinite. Okay, so even if your wire is infinite, the field, okay, that is associated, at any distance from the wire, okay, a non-zero distance, it is not going to be infinite. It tends to blow up only when we come very close to wire. Okay, if you remember, obviously we have already seen that the magnetic field, varies with respect to the, it varies inversely with the distance between the wire or the charged particle and the point at which we are finding out the field. Okay, so if we come, if suppose this is your wire, okay, and we start from here, and this is an infinitely long wire, okay, it extends. I'll just draw it here. Okay, it extends below also, and it extends up also. Okay, so at any point, if we consider here, okay, so this would be, the B is going to be, if you consider, so B is, proportional to 1 upon R square. Okay, so if we keep reducing the R, okay, so your magnetic field is going to, keep increasing if we keep reducing R. So then that is why we say that it tends to blow up only when we come very close to the wire. The field is directly proportional to the current and inversely proportional to the distance from the infinitely long current source. Okay, so this is, the physical understanding of this statement. So there exists a simple rule to determine the direction of the magnetic field due to a long wire. This rule is called the right hand rule. Okay, so now if this is your wire, okay, and you are holding this in your right hand and your thumb is, in the direction of the current. Okay, suppose your current is flowing in this direction, okay, along the wire in the upward direction, and if you hold the wire such that your thumb is, kind of in the, it is pointing in the direction of the current, the fingers are going to point in the direction of your magnetic field. So your fingers are going to curl in the direction of the magnetic field. Okay, so we, as you understand, like over here, okay, so this is your current. Sorry, this is not the straight wire. Okay, over here. Okay, consider this to be straight. Okay, and if your thumb points in this direction, okay, and your magnetic field will be in this direction, okay, in the direction where how your finger is going to curl. That is why over here you can see that the magnetic field is going inside the paper, and if you consider a point over here, okay, your magnetic field is going to be in this direction. So at this point the field will be denoted as 0, sorry, as a dot, and at any point, next or the right hand side of the current carrying conductor, anytime, any point that you consider, the magnetic field will be considered, it will be denoted as a cross. Okay, this is owing to the right hand rule that we see. Okay, so these are the few of the important implications that we see in the from the Ampere's law. Okay, so what was the first thing, that at any point on the, if we have a, kind of a, if we are considering, a straight line or wire, okay, and the wire is, suppose say along any axis, okay, so you are going to get these circular, kind of loops around the wire. Okay, so at any point, okay, on one circle, okay, the magnitude of the field or at any point in this circle is going to be equal. Okay, and similarly at this closed loop, the magnitude of the magnetic field is going to be the same, okay, but the magnitude at this closed loop and this closed loop will be different. Okay, but with respect to each of the loops, the magnetic field at any point on these loop is going to be equal to each other. Okay, and the direction of the magnetic field at any point in these loops is going to be tangential to the circle. Okay, so this is the second thing that we know, and because of this, obviously we have seen that magnetic field actually occurs in concentric circles. Okay, and the direction of the magnetic field can be given by the right hand rule. Okay, so that is if the thumb points in the direction of the current, okay, so your curling fingers, okay, the direction of your fingers curling is going to give you the direction of the magnetic field. Okay, so magnetic field is like this, and these again would appear to be tangential. Okay, so these are all the implications that we see. And one more important fact or inference that we get from the Ampere's law itself is that if you come closer to the wire, okay, your field is going to increase. Okay, that is your distance from the point of interest to the wire. If it starts decreasing, your magnetic field is going to keep increasing. So your magnetic field close to the wire is going to be much more than the magnetic field that we see suppose at this point. Okay, so these are the physical significance or implications that we find with the Ampere's law. So with that we can say that the Ampere's law, okay, so Ampere's law is to Biot-Savart law, that Gauss's law is to Coulomb's law. Okay, so Ampere's and Gauss's law both relate to a physical quantity on the periphery or boundary. Okay, for Gauss's law we used to consider different kinds of surfaces. Okay, we used to find one infinitely long cylinder or arbitrary shaped surface, and we used to find the electric field with respect to that. For Ampere's law again we consider closed loop that is also that is enclosing a surface and the current is flowing through that surface. Okay, so that is why we can say that Ampere's law and Gauss's law, both of them relate to the physical quantity on the periphery or boundary to another physical quantity, namely the source. Okay, so in Gauss's law it is related to the electric charge that we are considering. In Ampere's law it is the current that is the source. Okay, so over here you can see we are considering the source as the current that is passing across the surface or closed loop. Okay, so it needs to be noted that the Ampere's circuital law, it holds for any loop. It may not always facilitate an evaluation of the magnetic field in every case. Okay, so even though it is it is giving you a very simplified representation of a closed loop which is carrying current, okay, it may not help in understanding the it may not always help you understand in the magnetic field in other kind of physical cases. Okay, and there is another thing that we need to know, that Ampere's law is it is holding good over here for steady currents. But suppose if we have an alternating current, then Ampere's law will also not be a good uh, law to be expressing the magnetic field in those cases. Okay, so we will stop here today with the Ampere's law, and next time we are going to learn about the solenoid and toroid. Okay, so we are going to understand how the these are two kind of devices or materials that we will see how the magnetic field and the electric field kind of interact and their principles, and we will try to also get the corresponding expression of the magnetic field related to the current that is flowing through these devices. So thank you.